Welcome back. We're talking about elimination. In this case, we have a molecule that has more than one beta position. And I'm going to highlight the beta position. One beta position is here, okay, because that's the alpha, the one that it has the halide. And this beta position is identical to the previous one. So I'm going to call them beta 1. And I have another beta position and it's going to be here. Okay, now it depends, which, it depends from where you pull actually a hydrogen, or you take hydrogen from the system, the position of the double bond, it will be different. Okay, so we have carbon here that it has 3 hydrogen. Okay, same thing here. That carbon, it has 3 hydrogen. And here we have 2 hydrogens there. Okay, so we said we're going to call those beta 1. And these two, we're going to call them beta 2. Now, if you remove hydrogen from beta 1, okay, so let's say this is going to be the beta 1. If I remove hydrogen from beta 1, one of the product that I will get, okay, here. So if I remove that red hydrogen, okay, I will get this. I will get double bond between that carbon. Okay, and then here I have a methyl. Okay, so I got a double bond. Okay, and the double bond started from this carbon. Okay, we remove this H. We share the electron with the alpha carbon and the bromide and left the system. So plus Br minus 1. Okay, and if we take an electron, hydrogen from beta 2. Okay, if we remove one from beta 2 this time, okay, which one? And one of these hydrogens, the product that we will get, it will be this. Okay, so we have 2 methyl group here. Okay, next we will have a double bond there, and we have an methyl group there. Okay, plus Br minus 2. So technically, I can get 2 different products. One, when the double bond started from first carbon, and then second, the double bond is somehow in the middle of a molecule. The question is, which one of this is more stable? Okay. Thermodynamically, we say the double bond should be between 2 carbons that they have more substituent. If you can form a double bond that has more substituent, that double bond, it will be more stable. And the name for it, it will be this. So product. Okay. So you got an alkene with more substituent. When I say more substituent, you have 1 methyl group here, 2 methyl group there, and that's a 3rd methyl group. And now, if you look to the first product, the first product, which we call it Hoffman. I don't know why I feel there is an H, and okay, give me a second. I think there is an H for the name. No, it's correct. Okay, Hoffman, and we call it Hoffman product. The Hoffman product, a double bond has less substituent. At least we can see that here we have 2 hydrogens instead of methyl group. And now, which one of this is more stable? Okay, as I said, the one that with more substituent. And so you get 2 product. One is Hoffman, the second is Zaitsev. The one with more substituent is the major product. So if I wanna summarize this reaction, I'll write it this way. I say, whenever the base, which base? This base, okay? Why that's going to be the base? Because the metal will have a positive charge. So this one will be minus 1. We will get 2 product. Okay. The double bond might be between these 2 carbon. Okay, if you put it here, again, you get the same product, or double bond might be there. So you get two products. First one, you have a double bond there. Okay, and I removed technically this hydrogen, beta 2. So if you go after beta 2, and beta 1, it will give you such a product. Let's say in the double bond, it will be here. Okay, highlight the double bond. Okay, if your double bond, it has hydrogen atoms instead of methyl groups, we say it's going to have less substituent, and the name for it, it will be Hoffman products. And thermodynamically, this one is less stable than the Zaitsev product. And remember, in each case, you will get bromide as an ion. So I'm going to say plus bromide. Okay. And this one, the top one, it will be the major product. And the Hoffman, it will be the minor product. Okay. Is there any way to increase technically concentration or efficiency of Hoffman product? The Hoffman product, they are sensitive to steric effect. Okay. Why do I say sensitive? Because we are taking we're taking hydrogen from here, from there. Okay. That hydrogen is sitting on a carbon that is a primary. And because it's a primary, it has less, steric effect, okay? Less steric effect. If we take it from there, okay, reaching that carbon is going to be easier, okay? And so again, let me rephrase my sentence. I don't want to confuse you. I have Hoffman product and Zaitsev product. Zaitsev product are more stable, and in order to reach those hydrogen to get Zaitsev product, you might be facing with a steric effect. Okay, if you increase the steric effect, either on the substrate or on the base, somehow you will be pushed to Hoffman product. You will be pushed to Hoffman product. Why? Because reaching primary carbon is so easier than a secondary carbon. Okay, remember, this is a secondary carbon. And let's go through some example. Okay, I have methyl groups. Those are methyl groups, and each methyl, it has 6 hydrogens. So kinetic says you have 6 hydrogens that they are identical. Okay, and if you remove any of this 6 hydrogen atom, you get Hoffman products. Well, here, the second beta carbon, it says if you take any of this hydrogen, the blue hydrogen, you will get Zaitsev product that is way more stable than Hoffman. How can I force the base to go after those hydrogens instead of these hydrogens? Okay, remember, this is a primary and this one is a secondary. Okay, one way, increase the steric effect. Okay, on which one? On the substrate by itself. So then reaching the second beta, it will be harder. Another way is how much is increasing the steric effect on the base by itself. If I increase the steric effect on the base, then the base is going to go after a primary carbon rather than secondary. For example, if it's ethoxide, this is the ratio between Zaitsev and Hoffman. Ethoxide is a small base. So this one, it will be a small base. And it's a 71% Zaitsev and 30% Hoffman. And what will happen if you replace the ethyl with tertiary butyl? Tertiary butyl is bulkier. And because it's bulkier, it will be harder for the base to go after this carbon. So the base now is going to prefer one of these carbons, hydrogens of one of these carbons, because they are primary, and in order to reach them, you don't need to deal with a huge amount of steric effect. Okay, so we can say those hydrogen are naked, and we can easily take them from the system. And if you use that base, now as you see, we kind of flipped the ratio between them. So it used to be 71% for Zaitsev. Now we went down to 28. And Hoffman went to 72. What if I make it bulkier? Okay. So what I did, next step, I'm going to add a methyl group to any of this technical carbon. So I'm going to make the change longer. So again, this is a tertiary, but I added methyl group to any of those carbon just to make it longer, and see what will happen if I do it. Okay, and if you do it, this time the Zaitsev product went down and went to only 80%, and we got almost full. Like as you see here, it says 92% Hoffman product. So anything that increases the steric effect on the base, it will favor the Hoffman products instead of the Zaitsev product. Hoffman products are like technically they will be favored kinetically. Okay, well, thermodynamic is favoring Zaitsev. Why I say kinetic is favoring, like based on kinetic they are favored, because you have six hydrogen there instead of 2. So if you talk about the speed, taking hydrogen out of taking hydrogen out of six, it will be way easier and faster than taking hydrogen from beta 2. Okay. Here we have the 3 example, and the question is asked specifically, go after E2 reactions. Okay, now first thing that you need to do, you need to highlight the alpha carbon. This is the alpha carbon, alpha. Next, highlight the beta. And which beta? Okay, I have beta 1 here, and that's gonna be beta 2. Okay, I have beta 1 is here, which is equal to this, and the second beta it will be here. Okay, beta 1 is here, is equal to this, and beta 2 it will be there. Okay, so if I remove 1 from beta 1, okay, remove hydrogen from beta 1, and the product will be this. Okay, so we had 2 methyl group here, they stay as they are. Okay, next we're gonna have a double bond there. So this is gonna be the position of the double bond. And whenever you remove hydrogen from beta 1, and if you remove hydrogen from beta 2, okay, and the product will be this. Okay, again, we have 2 methyl group here, we have a methyl here, but now the double bond, it will be there. Okay, this double bond, this alkene has more substituent. Okay, so the second one, it will be the Zaitsev product. This one, it will be the Hoffman. Again, if we go after beta 1, we will get such a structure. So we will have a double bond here. Okay, and this one, it will be the Hoffman. And if we go after beta 2, and beta 2, we will have 2 methyl group here, and then double bond there, and then let's see, this one lost. Okay, this one has more substituent than that one. Okay, so the second product, again, it will be Zaitsev product, and the first one will be Hoffman, and this one is more stable. Okay, and again, this one is more stable, or the major product. Okay, And I'm changing the base to bulky group, and this time instead of an ethoxide or hydroxide, there are smaller bases, and we are switching to tertiary butoxide. Tertiary butoxide is a bulky group, and this is the tertiary butoxide. You have a carbon. Okay, we have a carbon that attached to oxygen, and our carbon, it has 3 methyl attached to it. So this is a primary carbon that it has oxygen, and oxygen, it has negative charge. Okay, so our base is bulky, and because it's a bulky, and it will prefer the primary carbons. Okay, primary carbons, and so that means it's going to go after beta 1 instead of beta 2. And so the major product, it will be like this. This time I'm going to say this one, it will be the major product, and which is going to be the Hoffman product. And the second one, if we go after beta 2, and we will get this. But I don't expect this one to be a major product, and or like the contribution is going to be really a small one. So I will say this one, it will be the minor product. And this one is the Zaitsev product. Okay. So this is going to be the major product. Okay. And so for the first and second one, because we had smaller bases than tertiary butoxide, the Zaitsev product, the second product, the one that was technically a product of elimination from beta 2 instead of beta 1, was the major product, because we get more substituent around the double bond. Okay, we have for example 1, 2, and here we have 1, and of course 1 hydrogen. So we have only 1 hydrogen. Well, there we have 2 hydrogens. Okay, so one side of the double bond, it has 2 hydrogen. Well, here it has only 1 hydrogen. It has 2 methyls there. And that's the reason I call this one with more substituent. And again, here I have 2 hydrogens. While this one, it has only 1 hydrogen down here, and it has 2 methyl groups and ethyl. So this one, it has more substituent. It will be the major product. And this, it has 2 hydrogens versus 1 hydrogen here. And so thermodynamically, the second one should be the major product. But because we use a base that is a bulky group, and that one is going to have huge steric effect, it will favor the Hoffman product, the one with less steric effect. And this is going to be end of this lecture, and thank you very much.